Is it reaching everybody? It's only this side. Would you say something for me?
1, 2, 3, 1, 2, 3. Okay. Should get this out.
as Ed or Dr. Ed or Lou or Dr. Edward?
Ed is fine. I don't really care. Honestly, I don't care.
All right. All right, we good? Jake, you good? That's live. I'm going to start the tell people about trivia. You good?
Welcome everybody to the new venue.
Yeah. All right. Hello, everyone. Welcome to Astronomy on Tap Seattle in our perhaps temporary, perhaps new location of Stute Brewing Capitol Hill. Thank you to them for hosting us. This is our 101st Astronomy on Tap. And as a reminder, we'd like to do a little trivia before our main event. So if you would like to participate in our trivia, please come up to the front, get a trivia sheet and a pencil so you can participate, and we'll run through a bunch of questions. So make sure to come up here, grab a sheet, grab a pencil so that you can participate. We'll start that in just a couple minutes. You can participate in trivia.
What's that?
You can participate in the trivia.
Oh, let me see how hard these questions are.
No one's sitting there, but this is all. So this is going to be used for in general, so that's why it's a bit easier. Like, if you have to move, it's public speaking. I can answer for myself, Jake.
Alright, I'll give it like 30 more seconds.
An interesting thing. I've never given a talk about.
Yes, I do. You want to know far away. We're mechanical engineers together.
We're going to start at 7. They're going to do a trivia.
sheet. I'll run through the questions once, slowly. I'll read them out loud, and then I'll run through them again quickly so you can look at them on the screen. And then after trivia, we'll have our wonderful talk, and then I'll give you the trivia answers after that. And you can try to see how many answers you can pick up during the talk, because we try to have them related to the talk that we're given. So, our first trivia question of the night is, which of the following missions did not include Dr. Edward Lu as a crew member? Was it STS-84 Atlantis, STS-106 Atlantis, Soyuz TMA-2, or STS-112 Atlantis?
I do know this.
That's good. That's good. What, 30 seconds for finish it? Question 2. During his 6-month stay aboard the International Space Station, Dr. Lu served as a member of which expedition? Expedition 5, Expedition 6, Expedition 7, or Expedition 8? Got a lot of information to go on in this question. There's some great numbers here. It's so true! As the kids say.
It's in the single digits.
Yeah, that's good. And if we get any of them wrong, you can also let us know.
I do know the answer so far for 2 for 2.
Yeah, that's good. Question 3. Is it B612? The B... Uh-oh. Oh, no, okay. I got it. The B612 Foundation, which was co-founded by Dr. Lu, takes its name from A, an asteroid Dr. Lu discovered during training, B, the asteroid home of the Little Prince in Saint-Exupéry's story, C, the orbital catalog number of the first tracked near-Earth object, or D, the original NASA project name for asteroid redirection. Question 4. A major predicting long-term asteroid trajectories arises from A, quantum effects on micrometeoroids, B, uncertainty in small non-gravitational forces such as the Yarkovsky effect, C, measurement noise from GPS satellites, or D, errors in planetary mass estimates. It's a very sibilant microphone. I'm getting a lot of... Yeah. I'm as a snake for Halloween.
These prizes better be good.
It's all relative. So if the questions are really hard, then the best score might be 3. Question 5. The ATOM platform, which will be showcased by the Asteroid Institute, is primarily designed to A, simulate atmospheric re-entry of spacecraft, B, model orbital trajectories and detect potential impactors, C, visualize telescope data in 3 dimensions, or D, analyze the mineral compositions of asteroids. Question 6. One major computational challenge in astrodynamics today is A. Limited precision of stellar catalogs. B. Handling massive data sets from survey telescopes in near real time. C. Lack of publicly available orbital software. Or D. Inaccurate Earth gravity models. All of the above. You gotta get Mond involved in this.
Obviously, he is right. Because obviously, all of our gravity models are wrong. Right?
Right, yeah. Because everything is wrong. Question 7. Asteroid mapping and tracking also have growing economic importance because A, they provide navigation for deep space probes. B, they identify potential targets for mining rare materials. C, they allow faster communication between satellites. Or D, they increase the lifetime of solar arrays in orbit. Well, I guess, anything can be growing if it starts low enough. Question 8. When astronomers determine an asteroid's orbit from telescope data, what is the typical first step? A. Running a Monte Carlo impact risk simulation. B. Linking multiple sky detections into a single tracklet set. C. Calculating its spectral reflectance to estimate its composition. Or D. Applying atmospheric refraction corrections to images. It's a lot of astronomy jargon words. Good luck.
I think that the correct answer to this question is not the intended correct answer. I think so too.
Now I realize. No, typical.
Typical? That's okay. That's fair. No one does this.
Question 9. The energy released by a 100-meter asteroid striking Earth is roughly comparable to A. The Hiroshima atomic bomb. B. A large volcanic eruption. C. A global magnitude 9 earthquake. Or D. A modern thermonuclear test.
What's the thermal?
Well, it...
All nuclear releases heat, right?
Exactly.
Fresh one.
That's why the Hiroshima bomb was left out, because it was so old.
And question 10. The term accessible astrodynamics most closely refers to A. Open source tools that let anyone simulate orbits online. B. Simplified equations for student learning. C. Launch trajectories requiring minimal fuel. Or D. Real-time mission control interfaces. And I'm going to go back through the questions quickly without saying them aloud, and then we will start our show.
All right, whiskey.
Chester said, the fans are doing too well. It's too many 7 out of 10s.
We gotta make it harder.
Median 4 tomorrow.
Yeah. It's a good thing the prizes are relative.
Yeah. Now we're going to pressure some of our audience. Pass her out. It's more of a joke in astronomy where people tend not to, but people do.
You can't really master out in astronomy.
The department could be like, all right, Mr. Paul.
They only recently let us graduate with a master's. Like, go to graduation. And by us, I mean the second years, or the third years last year.
I'm not sure. I wasn't really listening.
All right. Thank you everyone for participating. Please come up and hand in your trivia sheets. We will grade them throughout the talk, and we're going to go set up for the main event. See you soon.
Okay. So,
Okay.
I need well, hey, yep, that's the first thing. Paperwork. And I need this. Can I just pull it on out? Go for it. Okay, and let's see if it works. There we go. Can I get the clicker?
There's the clicker.
And I will test the, yep, we're good to go.
Nice.
All right.
And then I'll introduce you.
Okay,
and you'll,
cool.
I have like a couple sentences from, the
Whatever
ride.
you want.
Anything in particular you want me to mention?
Whatever you feel like.
All right.
All good to me.
So where'd you go to high school?
What's that?
Where'd you go to high school?
Webster, R.L. Thomas High School in Webster, New York.
Oh, really? My grandparents are from Webster.
Are you serious?
Yeah.
Webster, New York?
Yeah,
Really? Wow. It's a small town.
it really is.
Wow, that's kind of neat.
Yeah, they lived on the end of Basket Road.
I know Basket Road.
Yeah, that's funny.
Grew up in that town.
Nice. It's a fun coincidence.
Yeah, it is.
I was there a lot when I was a kid.
Oh my God.
Visiting them there.
Wow, that is pretty neat. Yeah. Do you know which high school they went to?
Nope.
There's two high schools in the town.
Okay. I could
One
find
of the
out.
50-50 shot.
All right. I will also warn you that this microphone.
Well, I'm on this.
So this mic is for a live stream, and this mic is for the read.
Oh, okay.
So
So I have to use both.
yes, sometimes the buttons on the bottom is a little finicky. So if it stops working, you just have to like push it up.
All right.
Yeah, Mario. Yeah. All right, now that we have collected your trivia sheets, it is my great pleasure to introduce you all to Dr. Edward Liu. He served as a NASA astronaut, which is very exciting, and he flew on, as far as I can tell, 3 Space Shuttle trips. And then after being an astronaut, he did some, weird things in the middle with Google. We don't need to get into that. And then he was one of the co-founders of the B612 Institute and the Asteroid Foundation, and now serves as their chairman and executive director, if I remember correctly.
Whoa.
Close. Well, he'll introduce himself, I'm sure, better than I can. So everyone give a big warm round of applause for Dr. Edward Liu.
Thanks. This is awesome. This is the first time I've ever given a talk in a bar where I can drink beer while I talk, which is completely awesome. So thanks to Sam and all the organizers for inviting us. It's really cool. It's good to be back in Seattle. Anyhow, so before I get started, I want to introduce my team, which is all sitting over there hiding in the corner. There's like 4 of them over there, I think. Colleen, you'll see Mario, the tallest of them, tallest astrophysicist. Joachim and Kathleen over there. I wanted to talk, I have to give a short plug for the B612 Foundation. What we do is we work on planetary defense, which is keeping this planet from being hit by large asteroids. We have a number of programs, including the Asteroid Institute, which is really the technical side of it, things. I'll talk a little bit about that. And then we have some outreach things, including the Schweikart Prize, which is named after one of my compatriots, a guy named Rusty Schweikart. He was the first lunar module pilot on Apollo 9. And he will be 90 years old in, I think, 2 days. So happy birthday to Rusty. Now, we've named a prize after him, and it's for graduate students, and I know there's a bunch of them out here, or postdocs who are interested in solving problems related to planetary defense, protecting the Earth from being hit by asteroids. So if you're interested in that, we have some information on it up here. Encourage you to apply for it. It's a cool prize. You get to meet Rusty. You get a really nice meteorite, and you get paid for your research. So kind of cool. So let's get started. So what I want to do tonight is, just because I'm really old and I've been in the field for a long time, I wanted to give some predictions. And you know the old phrase, which is predictions are always hard, especially about the future. And so what I would like to do is make public predictions, and you can all judge me in a few years whether or not they're correct. And because I always thought that the real mark of somebody is actually knows what they're talking about is that they're willing to make public predictions and be measured against them. So here we go. So let me start with how I ended up here. So these are pictures from my childhood. I'm the one in the little hat there. This is my brother and sister, my mom and dad. This is back in outside of Boston, Massachusetts. And then we moved shortly thereafter to a little town in upstate New York. Both my parents immigrated to the United States from, my mom's case, via Taiwan, my father's case from near Hong Kong. After the war, they met as graduate students in the United States and stayed and had 3 kids. I'm the middle kid. That's me right there. It's my older sister, Lisa. And I got a younger brother who's not yet born. So that's how I ended up here. Fast forward a bunch of years. This is an image of my second flight, the launch of my second flight. I just like the picture a lot because this is roughly as we're roughly going supersonic. You actually get these condensation clouds a little bit before you hit supersonic. So we're probably going, this is probably about 15 seconds after launch. We're probably at about 500 miles an hour. This window right here is where I'm sitting. And if it wasn't covered up by this, you could see my helmet through there. This is one of the pictures I really like a lot. It's actually not of me, but it's a picture taken by me. Although I'm in this picture because the top of my helmet is right there, reflected in my crewmate's visor. Just a picture I like. It's what it looks like after you land in the Space Shuttle. That's Atlantis, and this is all of us. It's about 4 in the morning, and you're doing a press conference on a 90-degree day in Florida, and the bottom of the shuttle is still warm. It's kind of a cool feeling. You put your hand next to it, and it's still glowing hot. Kind of cool. A picture I like, just because it's of sort of this area here. I live here, near San Francisco. This is Baja, LA. This is Central Valley. We are right here. And on a typical day, you can see from Central Baja all the way up to Oregon. It's kind of a cool. It's a cool experience. Just a picture I thought was fun because it's of the Middle East and it gets you to think about the fact that north is not always up in pictures. So this is the Nile River. Luxor is here. Big giant triangle here. That's the Nile River Delta. It looks like a delta. Looks like the letter, the Greek letter for delta. You see why they came up with that. When you see images of the Earth taken by astronauts, there's an awful lot of the Middle East. And it's not necessarily because it's the most interesting geography, but it's actually because there's very few clouds over this part of the world. And if you try to take a picture of Seattle, good luck. Giant Category 5 hurricane. It's kind of cool flying over the top of this thing, looking down. You could see tornadoes spooling off the wall of the inside of the eye. Sunsets, sunrises. Every astronaut who gives a talk talks about these things. Get to see 16 units a day as you go around the Earth. Okay, so let's get over that. So that's how I ended up here. That's why I was an astronaut since 1995. Left NASA after 12 years in 2007. Been involved in space ever since then. So basically, I have 30 plus years experience in the field. So I feel like I have some background to give stupid predictions about the future. Again, come back in 10 years and decide if any of this makes any sense or is correct or not. So the first prediction I would like to make is that we have entered a really interesting period in space industry, space development, everything to do with space. We've hit what I believe is a point where we're growing exponentially. So let's talk about that. What do I mean? And why do I believe there'll be more than 50,000 satellites by 2028? That's only in 3 years. Now, as late as 2018, there were there's about 900 active satellites then. Okay, so enormous growth, right, in a decade's time. So let's look at some actual data. You can go online, Our World in Data. It's a great website. You can plug in anything you want, and if there's data on it, you can plot it. Highly recommended. But if you plot number of objects, which is really satellites launched into space, it's flat, 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 flat for many years. Look at the upper line. That's the entire world. And around here, 2016-ish or so, something changed. And it turns out a lot of things changed. So let's plot this, as all right-thinking people do, on a log scale. And as everybody knows here, it's a quiz on your math skills. When you have an exponentially growing thing on a log linear plot, what do you get? Straight line, right? So if you have something that looks like a straight line, it's exponentially growing. That means it's e to some power, okay? And the blue line here is an exponential, it's just a straight line drawn on here across that same data, but now look at this as an exponential scale. 2022, there are a little over 2,000. I think this year we will hit close to 6,000. So, you know, it's not that many years that we've been on this, but the slope of this line is a doubling every 2 years. And that should sound familiar to people in this general area, because a doubling every 2 years is what's also known as Moore's Law when it is applied to sort of information technology, let's call it. Right, and that's the thing that's driven everything about, you know, Seattle to begin with, but most of California. The industry's changed our lives, right? It is because the amount of processing that you can buy for a unit cost doubles every 2 years, which is why my cell phone that I have in my pocket here is, which is now 6.5 years old, is an absolute piece of junk. My teenage kids laugh at me. They laugh at my phone, but they're like, you can't even download a lot of apps. They just don't run on it anymore because it's 6 years old. And that's because there have been 3 doublings in sort of computational capability since then. So it literally is a piece of junk. And I will replace it this year because there's a lot of apps that just don't run anymore on my phone. And the consequences of all this is that our lives have changed because there is an industry in which things double every 2 years. So if you believe this chart, which again, this is just the raw data, we're in this phase now for space, at least if you measure it by number of satellites launched. Now, there's a lot of ways to measure the health of the industry, but this is just one metric. In the same way that when people talk about Moore's Law, they talk about number of transistors on chips, or they talk about speed, various things, but however you measure it, pretty much things are exponentially growing. This was first pointed out by one of the founders of Intel, a guy named Gordon Moore. And he wrote a paper about it back in the 60s, pointing out that, so somebody else named it Moore's Law. But when he first wrote that paper, it was after only 4 doublings. It was only 8 years after that curve started exponential. So we were actually beyond that for the space industry. Now, he didn't know it was going to continue, and we don't know that this is going to continue, but I can tell you that, here we are in 2025, this curve does continue, and it is up here where I'm pointing up on the ceiling right now on a log plot. And in his seminal paper, Gordon Moore talked about what if this continues? What are the consequences? And the consequences are pretty interesting. First off, if you're a scientist working in the field, you got to move fast. You cannot spend 3 or 4 years thinking about, or an engineer working on developing something that in 2 years is obsolete, right? So you need to be thinking speed, speed, speed. If you're an investor, you shouldn't be thinking about investing in projects that have a 10-year timeline, because you're 5 doublings away in terms of the basic technology, and things are going to change. And if you're a business on that, you should make business plans that are on 2-year timescales, not on 10-year timescales. Well, the space industry has not, up until this point, operated like that. We have 10-year plans, we have 20-year plans, and I think those are all obsolete right now. And there are a lot of space companies up here. There's a lot of aerospace companies up here, and my warning to them is, you better think about this. You better not be looking at your grand 10-year plan to build something, because it is going to completely fall apart in 4 years. Because you can't predict what's going to happen. Because remember that a doubling every 2 years is 5 doublings in 10 years, which is the same as a 3,200% per decade growth rate. And that's what we're looking at right now. So a lot of consequences for this. Okay, the next thing I want to talk about is just to show this, what it actually looks like. This is I started another company a few years back called Leo Labs. We build radars. These red things are the cones that we operate. But these are all the satellites we were tracking. This is as of 2024, so it's almost a year ago I downloaded this. Obviously, the satellites have blown up to be much larger than they really are, so that you can see them on the scale of this. But there's a lot of things going around the Earth right now. And in fact, since this was downloaded a year ago, there's 40% more than this. Because again, a doubling every 2 years is 40% a year, or 1.41 per year, right? So my next prediction is that we're going to discover millions of asteroids. Why is that interesting? Well, a lot of people here are working on this particular project, and the reason I think it's going to happen is because of this telescope. So some of the people out here are directly involved with this. I know there's probably some people here. This is the Vera Rubin Observatory in Chile, which has recently come online. So it's still in the commissioning phase, but this massive telescope has an 8.5 meter, so almost 27, 28 feet across main mirror. And it's roughly 2 orders of magnitude more sensitive to tracking and discovering asteroids as all other telescopes combined. Why is that interesting? What is so interesting about the fact that we're going to discover millions of asteroids? So I'll talk a little bit about that, but I have to give a little quick plug as to the kinds of things that our institute does, which is we are working with the Vera Rubin Observatory and the world community to turn essentially photons hitting the telescope, hitting the detector, turned into data, ones and zeros, into understanding of the solar system. It's calculating orbits, understanding distributions of things, and in particular, we want to know if any of these asteroids is going to hit the Earth. Okay, because obviously that's a bad thing. So one of the things we realized is that this whole business of discovering asteroids is really, if you think about it at heart, one of mapping the solar system. Now, the vast majority of objects in our solar system are not planets. There's just a handful of planets, 8 or 9, depending upon who you ask. but there are millions of asteroids. So nearly every cosmic body, every small world in our solar system is an asteroid. It is not a planet. So we're a little bit lucky we live on a planet here, but most of these asteroids are, as it turns out, circling the sun between Mars and Jupiter, although there's a large number of those that get thrown out of that orbit and that end up in the inner solar system where they can hit the Earth. So why is mapping the solar system important? So I'm a bit of a history buff, so I want to show this kind of cool image. This is a map called the Cantino Planisphere, and it was made in the early 1500s. I think it was, oh, there it is, 1502. So this is only 10 years after Columbus. A couple cool things on this. They got Africa mostly right. India, obviously they got Europe right, because this map was made in the Netherlands. And then stolen by I believe the Portuguese, and then stolen again, sold and whatnot. But you see, they got already parts of the Caribbean, and this is South America here. They obviously missed most of North America, and obviously didn't know a whole lot about the Pacific Ocean. But they'd already gotten pretty good by 1502. So if you remember back to your elementary school history lessons, around this time, nearly all the great powers invested a lot of their treasure in making maps like this. Why did they do that? Well, there's three main reasons why. You can sum it up as fear, greed, and curiosity. So fear, one, there was a competition between the great powers, and whoever had the best maps had an advantage from the standpoint of a military advantage over, Spain versus Portugal versus England versus Italy, etc. Number two, they were interested in trade routes, so commerce. So if you had the best maps, you had an advantage from the standpoint of commerce. In fact, the very first worldwide corporation, which is called the Dutch East India Company, first sort of international corporation, their principal advantage in the 1500s was they had the best maps in the world. And that allowed their ship captains to do things that nobody else could do. And that corporation lasted for nearly 200 years. I believe it was the longest lived corporation of its type, international corporation, in human history. And it was built upon having the best maps. And last, if you have the best maps, you can also understand the geography of the world. So why might we be interested in mapping the solar system? Well, number one, so let's go to those three motivations: fear, greed, and curiosity. So fear, protection. So we here on Earth sometimes get hit by large asteroids, and if you know where the asteroids are and where they're going, I should be able to predict when an asteroid has a chance of hitting the Earth, and I can do something about it. So that's the fears part. The greed part, the commerce part. Well, at some point, if human beings do move out into the solar system, and I believe we will, because of those first charts I showed you about the rapid growth in the space industry right now, the location of most of the resources that are accessible in our solar system are actually on asteroids. You don't want to drop into the gravitational well of a planet and then climb back out. It's much easier to get them off of asteroids. And last, from a pure science standpoint, understanding the distribution of the locations of asteroids and their orbits tells us how the solar system formed, how the Earth formed, and how we ended up where we are. So for the same reasons, I believe we're going to map the solar system using those millions of asteroids discovered by Rubin. So let me give you a little video of where we are today. These are the asteroids in the JPL database. So this is most of the asteroids that we know of. There's the Sun. There's Mars, color-coded red. This is Jupiter's orbit. This is the asteroid belt. The Earth is this light blue line. And you can see, how many asteroids they are. And this is actually all actual real data. So here's the Earth. We'll zoom in on it. And the date of which this is right here. This is 2022 at this point, but I've sped things up. Here's the Earth. You can see the moon going around it. So again, all anatomically correct. There we are as you zoom in. This is kind of a cool program. It's called Open Space. It's an open source program. You can plug all sorts of large databases into it. There we are. You know, this date does correspond to the locations of the continents on the Earth, although it's spinning so fast here, given the speed up in this. But I like to actually look at this when I'm home in my office sometimes. I like to put this on as the background of my computer. I have a nice big monitor. I just think it's really cool to remind yourself just how much stuff is flying around in the solar system. This reminds me a little bit of that image of the satellites going around the Earth. There's a lot of these things. And over the next 10 years, the Rubin Observatory is going to help us multiply this number of asteroids that are known and tracked by roughly a factor of 10. So here's my next prediction. When we build this map, and over the next 10 years, we are going to find asteroids that have a very high chance of hitting the Earth. And what'll actually, when we say high chance, what we mean is that we will be able to measure its trajectory, we'll calculate its orbit, we'll be able to predict it forward for many, many years or decades even, and know that a particular asteroid has a chance of hitting Earth. And given the uncertainty in it, you can translate that into a probability of it hitting the Earth. And then I think we'll be able to do something about it. So some of you may have read about, early part of this year, there was an asteroid called 2024 YR4. It was discovered at the end of 2024, so i.e. around Christmas time of last year. And it was known to be coming very close to Earth on December 22nd at roughly 12:29, I think it is, UTC, in 2032. So that's 7 years from now. So close to the Earth that it actually had a 4% chance of hitting the Earth. And one of the things we were able to do is to run Monte Carlo simulations from the orbit of that asteroid and show that if it was going to hit the Earth, it could only hit the Earth along a particular line, which ran through some interesting cities. Lagos, Nigeria, population 20 million. And Mumbai in India. And this asteroid is about 60 meters across, which would give it an impact energy of around 10 megatons. So a little bit larger than the one that created Meteor Crater. If anybody here has ever been to Meteor Crater in Arizona, if you haven't, you should go. It's a really cool place. It's a giant hole in the ground it's now about 500 feet deep, but it used to be about 700 feet deep. And it's about 1 kilometer across. And that was a smaller asteroid than 2024 YR4. So obviously that's not something we want to have hit the Earth. Luckily, we were able to shrink the uncertainty region by getting observations of it with the James Webb Space Telescope. And with the result of those late-breaking observations, which was about 7 months ago, 6, 7 months ago, we were able to actually rule out it hitting the Earth. However, now we know that it's an interesting case because this long line, if you extend it out, actually went through the moon. It actually has a 4% chance of hitting the moon. It's going to come within a few tens of thousands of miles of hitting the moon on that same date at roughly that same time. So we can discuss later whether or not we should deflect that from hitting the moon as a practice test of how you would go about this. It's in some sense like the universe has given us a preseason game, which is real enough. You go through the motions, but if you lose, it doesn't count, right? So it's a nice test case of can we protect the Earth from an asteroid which is actually headed towards the moon by practicing on one that is going to hit, or from hitting the Earth by practicing on one that's going to hit the moon and it doesn't show up on our regular season record. So my prediction is that Rubin is going to discover enough asteroids that are going to come close enough to the Earth in the future that we will have to consider deflecting an asteroid. And I believe we're going to actually do it at some point here in the next, call it, couple of decade or so. Let's go back to some of those pictures. This is one of the reasons I think about this a lot. It's a picture I took of the moon above the, very, very zoomed in picture of the moon above the atmosphere of the Earth. And if you spend enough time staring at the moon from orbit, you think about all the craters. In fact, you can't even count all the craters on the moon because there's craters on top of craters that have erased other craters, right? And then if you just think about it a little bit, you say to yourself, wait a second. The Earth has stronger gravity than the Moon, so on per unit area, we have more asteroid impacts on Earth than there are on the Moon. You just don't see them because of clouds, weather, atmosphere, oceans, those sorts of things. But the Earth has been clobbered a lot of times. We have had multiple mass extinctions. The one that wiped out the dinosaurs is just a famous one, but there have been many, many mass extinctions in the fossil record, and it'll happen again unless we do something about it. So at this point in human history, from this point forward, if an asteroid hits the Earth and wipes us all out, it's not bad luck. 100 years ago, that was just bad luck because there was nothing we could do about it. But now that we can do something about it, now that we have telescopes, now that we have the mathematical capability to calculate these orbits and know in advance when something's going to hit the Earth, it's no longer bad luck if it happens, then it's kind of negligence on our part. So I believe we will deflect an asteroid. I just like this picture. Whoops, let me just show a fun picture of, this is a asteroid impact crater in, it's north of Montreal. It's typical northern lights over Canada, but this is almost 100 kilometers across. It's just one of many craters that you can still see. This is not quite the size of the one that killed off the dinosaurs, but it would have been a very bad day on Earth when that hit. 100 kilometers across or so, something like that. So how do you deflect an asteroid? This is video taken by the onboard camera of a mission called DART, Dual Asteroid Redirect Test. It was a mission flown, sponsored by NASA, carried out by the Applied Physics Laboratory. It's been about 3 years, and what we did is we deflected this asteroid, which is part of a dual system. There's two asteroids next to each other. We deflected this one by running into it with a small spacecraft. The spacecraft was smaller than this table. I mean, the array stuck out, but the main part of the thing was just a few hundred kilograms. And we ran into it at about 6 kilometers per second. And that little bit of momentum actually changed the orbit of it, changed the velocity of this by, it's a few millimeters per second. Not a lot, but it turns out that if you want to prevent an asteroid impact on Earth, the typical change in velocity that you need to impart to an asteroid to keep it from hitting the Earth is only a few millimeters per second. So we know how to do this. Okay, now we haven't done it on an asteroid that actually, where you don't get to choose the asteroid, where you don't get to choose the date, you don't get all these other things. So we're not quite there, but the basic technology, I would call this, if 2024 YR4 is the preseason game, this was the practice. Okay, and so we have a rough idea of how to do this. For those who wonder why it takes such a small change in velocity to make something miss the Earth, Earth's pretty big. The answer is that the Earth's a moving target. Here we sit on planet Earth, which is presently moving 65,000 miles an hour around the sun. And if the impact date is 7 years off, the Earth is going to be in some other location, right? And all you have to do is upset the timing a little bit such that the asteroid and the Earth still go through the intersection, but a couple minutes early or a couple minutes late, the asteroid arrives, so it just misses the Earth because the Earth is essentially running the red light through the intersection. So I think in the next, call it 10 years, there will be an asteroid deflection mission mounted. And we'll just have to see what Ruben finds, but it's given the number of asteroids that we're going to detect and the odds of them ones coming close, I believe we're going to deflect an asteroid from hitting the Earth. And I think that'll be one of the most important space missions ever flown. I think it will gather a lot of attention, and it will be a good thing for us to do, just because you don't want the first time you do this for real to be when it actually counts. My next prediction is just based upon all the sum of this, which is that I think that human activity in space is going to be commonplace. And the reason for that is essentially that Moore's Law growth that we're seeing right now. We're seeing investment, we're seeing startups, we're seeing fast motion, and we're seeing progress in space right now at a level that we haven't seen before. And it's a self-feeding flywheel. The more people invest, the more they expect to see results, the more profits there are, the more people get into the field, the more people invest, etc. And I think that's going to happen here. And if there's one thing that's true, whenever you ask people how much progress they expect to see in the future, they always overestimate it in the short term. They go, by a year from now, we'll have solved this, this, and this. They're always overestimating. But they always underestimate it on decade or more time scales, because they don't think about the things that have exponentials in them. Because an exponential, the short segment of an exponential looks like linear growth. And my prediction is that over the next few decades, we actually will see human activity throughout deep space, not just surrounding the Earth, not just at the moon, but I believe that's going to happen. In part, it's due to this beast, but there's others too. It's not the only one. This is the Starship, which was a very awesome launch that we saw last week, and I believe this is going to change things. It's going to drop the cost of launch per kilogram another order of magnitude, and the fast followers, the other competitors of this are going to do the same. They won't be the only ones doing this. And that means that, now this is a little of a longer prediction. I think this is now multiple decades, but I do believe that human beings will become a spacefaring civilization in the same way that human beings went from, living in your little town your whole life. In 1500, the typical human didn't venture more than 30 miles from where they were born to where we sit today. The same thing is going to happen in the solar system, and that human beings that travel and throughout the solar system will at some point become commonplace. I don't believe this is measured in centuries, but I actually believe it's measured in decades. Just wanted to end this with a short story. This is a picture taken from the flight deck of the Space Shuttle when the Space Shuttle is upside down and flying backwards. So this is the overhead windows. These windows right here are actually looking straight upwards. Those two are looking back into the payload bay. But we typically flew the Space Shuttle upside down and backwards because of space debris. If you don't want to get hit on the front windows, but if you got hit on the back windows, it's okay. Or less bad, let's call it that way. And on the last evening of my very first flight, we were all done with the entire mission. You have to pack everything up, get everything ready for landing, and then you basically have nothing to do. We were going to land the next morning, and so you actually have a little bit of free time. And we were having this view, and my crewmate, a guy named Jean-Francois Clairvoy, a European Space Agency astronaut, who goes by the name of Billy Bob. Billy Bob's a funny guy. He was a bit of a philosopher. And he said, well, let's be upside down tonight. Let's eat our dinner upside down. So we were sitting on the floor here, or floating like this, kind of with our feet pointing this way. And at some point, you could make the transformation in your brain that made it look like you were in a glass-bottom boat. If you've ever been on one of those overlooking, like going over a reef or something like that. And it really looked like that. The Earth going by below you looked like we were sitting in a boat. We were sitting there eating our dehydrated spaghetti or something like that, and Billy Bob says to me, he goes, sometimes I think, wow, the world is enormous. Look how big this is. You could see the Milky Way when we went over to the dark side of the Earth, and then we would come back to the light side of Earth. We were sitting there for a couple hours eating our dinner, and he goes, the universe is really big. It's amazing how small we are. Other times I think, wow, we're inside a spaceship built by human beings. We're going nearly 18,000 miles an hour. Humans are really big. We can do almost anything if we put our minds to it. And he goes, yeah, I guess both are true. And I always remember that because I think this really is the case. You shouldn't forget how big the universe is, but you shouldn't forget what we human beings can do if we really work on something together. And I think we've got a lot of adventures to come, a lot of development to come, and I don't think we can predict very well what those are going to be. because things are changing so rapidly. But I can say this, that I think in 20 or 30 years we won't recognize, there'll be crazy surprises that happen there, including, I believe some of these things that I predicted here are going to happen. We'll be seeing tens of thousands of satellites rather than just a few. We'll be finding millions of asteroids, we'll be mapping the solar system, and we'll be deflecting something from hitting our planet. And already that's pretty good. So I'm looking forward to seeing the next few decades. I hope I live to see a bunch of them. And thank you very much. Okay, here's the deal. I will answer any question about anything as honestly as I can. So if anybody has a question they want to throw out about anything, I'll take it. So, but you got to shout it out loud enough, and I'll try and repeat it. Is there a negative downside to this rapid growth? It's got to be lots. Just like there was downsides to us, building cars, or there's car accidents, there's pollution, there's stuff like that. There's downsides to everything that humans do, but there's also upsides. Life's a lot better now for us than those poor saps living in the 1500s, right? They're dying at age 28 and they were old, right? They were dying of bubonic plague, right? So nothing doesn't have consequences, I think. But I don't think that's a reason for not making progress. That's how I feel about it. That's just a member of society. But that's my personal feeling. And actually, I think a lot of people here may feel the same way, because I think that a lot of people involved in technical fields, a lot of scientists, do have this dream of the big future. Well, we'll see where we can take it. Okay, how about over there? How long until Kessler syndrome infects the orbit? Well, Kessler syndrome, to those who don't know, is this idea that if you put enough orbiting satellites around the Earth, they start to run into each other, and then they create debris, which then nobody's driving the debris. The debris hits other things, and it cascades into it's what forms planetary rings, for example. Now, I think we're going to be smart enough to avoid it. Right now, we're orders of magnitude away from it being an issue. But most of these satellites are somebody's driving them, meaning they can avoid collisions. And we are good enough now at tracking objects in space that we can actually give warnings of objects that are just debris. So I actually don't think it's going to be an issue, but I believe it's going to be in the same way that we have air traffic monitoring and rules and regulations for flying aircraft today that we didn't have in 1910, when if you wanted to fly someplace, you just did, right? Anywhere you want, just go. That's not the case today, but the same things are going to have to take place in space, and they are. So, how about over here? Oh, hi. Good question. It was about the role of future astronauts and the risk. Is it worth the risk of having people out there? By the way, Soyan, sitting next to you, is a Korean astronaut. So thank you for coming to my talk. But so I think that the role of human beings is more than just as workers, as to do something. You're not there as, in the same way that, what's the point in getting in a plane and going to visit Paris? Is it the same as if somebody shows you pictures of Paris? Were you there? I mean, does it, or have you really experienced it? And a part of being a person, I think, is experiencing things. And I don't think that's going to change. So I think that, yes, there are people whose jobs it will be to fly things or to do things, construction or whatnot, probably on places other than Earth at some point. But part of the reason for going places is so that people can be there. I think. Okay, how about back here? I'm sorry? Oh, Carlos Noriega, yeah. Yes. Carlos Noriega was a crewmate on my very first flight. Carlos was in my class. He's a really good friend. Awesome guy. He grew up in Peru, actually, or was born in Peru. Are you from Peru? Yeah. And ex-Marine Corps guy with a computer science degree. And probably the most organized person I have ever met. He put everyone else to shame in terms of his ability to be organized. It was uncanny. So. Okay, over here.
So typically, governments have pioneered space exploration, and the commercial sector has followed up with the economic intention. Do you think the commercial sector might overtake governments in exploration in the upcoming decades?
Yeah. So the question was about how the government started, typically has underwritten the cost of space exploration, and will the commercial sector eventually take over? I think a good example for that is in the electronics industry. In the 1960s, the building of semiconductors was dominated by government as a customer. It was for military and for the Apollo program. But we reached the point pretty quickly even by the late 70s where the commercial uses was far larger. And today, the commercial uses of electronics and semiconductors completely dominates over government-funded things. And so we're watching the same thing happen in space, in that those satellites launched I showed you, it is probably more than 90% commercial right now. In terms of the satellites launched this year, probably well over 90% are commercial, not government of any sort. So I think we've already hit that point, and at this point I don't think there's any looking back. Sure, Ben?
When will a tourist flight to orbit for a day and come back cost less than $10,000?
When will a tourist flight cost less than $10,000 to orbit, not... Oh.
One day of orbit and come back.
Okay, it's going to happen on a Tuesday. I can't tell you when. No, which year, but eventually we saw this thing happen in aviation, right? Where, I mean, in 1910, who flew on an airplane? Very rare. Whereas now, it's rare to find somebody who hasn't flown on an airplane. And I believe the costs are going to come down. It could take a while. I mean, that doesn't, even though if you looked at the cost in the 1950s of getting on an airplane and flying to Europe, for instance, still very expensive. It's not like your typical person did that in 1955. And the same thing's going to happen, I believe, for space travel. It's going to be the province of, wealthy, or people who have a job to do, sponsored by some company or something like that. But eventually, it will get to the point, I believe, where cost will come down. Because if you look at the raw cost of flying a space vehicle, the fuel's actually cheap. The cost of a space launch is only a couple percent at most the cost of the fuel. And that's the lower limit. So I think we'll get there. So if I had to take a guess, I'll say 25 years. And base that on, 1945, end of World War II. A lot of people were flying on airplanes in World War II. Mostly they were military pilots, or they were troops going to someplace, right? But by 1970, a lot of people were flying on now jetliners, and deregulation was happening, and that really brought prices down. And I think we will see similar things, but give it a couple of decades at minimum. You can come back in 25 years and see if I'm right. Over back there? What did I think of? I'm sorry, I missed it.
Don't look up.
Oh, the movie Don't Look Up. Oh. No, it was kind of a funny movie. I did laugh. But, I don't take a whole lot of lessons from movies. about physics or policy or anything else. They're fun. So, how about over here? The interstellar comet 3I Atlas. Okay, for those who don't know, this is an asteroid that's been observed, and we know that it didn't come from the solar system because it's moving too fast to have originated in the solar system and been accelerated by the sun's gravity. So that meant it had to have some velocity coming into the solar system, which meant it came from outside the solar system. And there are, I'll say it, ridiculous articles in the press, egged on by scientists who I believe make it a bit of a fun game to try and spur ridiculous articles in the press, which isn't that difficult to do. I believe some of these scientists are saying things that they turn around and laugh and go, let's see if I can get anyone to believe that story, even though it's not aliens. Although, if it was aliens, I wouldn't tell you, right? Just kidding. Mm-hmm. The best and worst thing the press has said about me, I don't think they've ever said anything bad about me because I don't think, given the large number of astronauts there are, Soyuz, that we rise to the level of the Apollo astronauts. I never had reporters following me around, for instance. So I think it's been fairly uncontroversial for me. Although I would say that in the 1960s things were very different. Mm-hmm. If space becomes more commercialized, what will happen to NASA, for instance? This is a very timely question because NASA has to decide what it wants to be when it grows up. And I think that's really the way to put it. Because what is their role? Right? They shouldn't be, in my opinion, running a bus or running like transportation. Because that's in the same way that the government doesn't run the airlines. Their airlines do a much better job of it because that's all they do. And I believe that the role of NASA ought to be to push the limits. Kind of what they did in the 50s and 60s, where they pushed, they did aerodynamics research, for instance. And they did, they calculated airfoils that the commercial companies could use, and they made tables of how all these different airfoils worked, and they spurred the industry. But they didn't build airplanes. They built test airplanes. They built X-planes, which were one-off, crazy ideas, type things. And I think that ought to be the role of NASA, which includes, by the way, a lot of scientific exploration. Because again, they should be pushing the limits. But they shouldn't be doing the more mundane things, I don't think. Because I'll be honest, large government agencies are extraordinarily inefficient. And I worked at one. I love NASA. But there's no way you would ever say it was efficient. And so for organizations like that, their role ought to be do the stuff that efficiency isn't the goal. Like if you're trying to run an airline, efficiency is the goal, right? Reliability is the goal. But if you're trying to push the limits of scientific research and so on, efficiency is not the goal. And that's where it's also difficult to make a business case to do things. So I think it's going to have to change. But nobody asked me. Mm-hmm.
What do you think about the regulation when it comes to safety critical development? Putting a human in a spacecraft is way more challenging for a lot worse than doing that kind of prediction.
Yeah, so it sounds like there's really two questions here. One which is, I think your main question is really about safety regulations for spacecraft. At some point, those are going to come in, but I don't think it's. I think it's a little premature right now, and the reason is because when you buy a plane ticket right now, you expect that that airline is safe because most people who fly in airplanes don't have any capability to judge the safety practices of an airline. And in the interest of commerce, it's good to have standards because then people can count on things, right? And whereas we're not at that point yet for space travel. And most of the people traveling in space have to be aware of the risks. So I think at some point you will have to have such things as safety regulations, but you shouldn't do that prematurely or you're going to kill the industry off. So, I mean, so for instance, every astronaut that went up, we knew the risks. I don't know if that is true for all the suborbital people who are going up today, although I believe they do make them sign these crazy waivers and they make them, and they make them read aloud, the part where it says you could die doing this. But it's definitely not at the point like, hey, I thoroughly expect that when I get on a flight and fly back home tomorrow, that they're not cutting corners. I do expect that they're not cutting corners, right? Because a lot of everyday commerce and everyday life depends upon these things not crashing. Whereas currently a trip to space is a bit like an expedition to the top of Mount Everest. A large number of people who do this die. And that's just part of what you sign up for when you say, I'm going to go climb Mount Everest. Right now, that is what you sign up for when you say, I want to fly into space. Okay, way back there. So the question is about what do I really mean by a spacefaring civilization, and what is the role of I guess space settlement, human beings living on other locations. I think eventually they become kind of similar. It's obviously going to take some time. Take for example the New World here. When Europeans came to this continent, we were looking at late 1400s. But before a lot of Europeans came to the New World, it was almost 100 years later. Now, I think things could develop a lot faster because technology didn't develop that quickly. A ship from 1540 didn't look that much different from a ship from 1560. So I think we're going to see, it could take a long time, but I don't think it's going to take 100 years. Just my guess. Over here.
What impact do you think AI will have on spaceflight in the future?
What impact do I think AI will have on spaceflight in the future? I believe what we're going to end up seeing is very, very smart robots. Robots that can do things without human intervention. And I think they're going to be a big part of not just space, but just everyday life at some point going forward, given the pace at which things are changing on the robotics and artificial intelligence front. Mm-hmm. In the most important scientific advancement in my lifetime. Oh, geez. Okay, are you talking a technical achievement or a pure scientific achievement? Both, okay. On the pure scientific side, in my lifetime, I think it's been the understanding of what's called the standard model of physics and the standard cosmology, which is the understanding of the evolution of the universe. We have a very self-consistent theory. It still has some holes in it, but it explains most everything we see, which is just amazing that we can do this. Even down to the creation of the elements, formation of galaxies, expansion of the universe. It's absolutely amazing that it works. Sort of on the technical side of things. I think in the last 60 years, it's been the rise of computers. And, you know, everything was analog almost when I was born in the early 60s. Certainly not the case now. And it certainly changed our lives. But just opinions again. Mm-hmm.
So you mentioned that like a small spacecraft to scooch an asteroid just a little bit and that's enough. Is there a tipping point at which an asteroid becomes large enough that the mass and velocity to scooch it is almost unfeasible?
The question was, you know, if you, even a small spacecraft can move an asteroid, but at what point is that asteroid too big to even do that? Well, remember that you don't have to hit it just once. You know, if the asteroid is large enough, and here I'm talking about probably a few hundred meters across, then yeah, it gets to the point where hitting it just doesn't do that much good. Now, if I ask the question, how much more common is an asteroid that, say, the size of size of a very large nuclear weapon compared to something that's 250 meters across? The distribution of asteroids is a power law, meaning lots more small ones than there are large ones. So you're likely to have to deflect 100, 50-meter asteroids before you ever have to deflect a 250 or 300-meter asteroid. That doesn't mean this isn't going to happen. It's a bit like, going to Las Vegas. At some point, your number comes up, right? Now, if you have to move something very large, like the kind of thing that would be like a planet-killing dinosaur, you're probably going to have to break out the nuclear weapons because the sheer size of these things is enormous. Like, for instance, the asteroid that wiped out the dinosaurs, roughly 10 miles in diameter. So when the bottom parts of that asteroid were hitting the ground, the upper parts are up above jetliners. You know, the other side of the asteroid is 50,000 feet high. There's almost no air up there. That's the size of the asteroid. You're not moving that with a small spacecraft, not significantly. Okay, now I should point out there's another interesting thing here. If you change the velocity of an asteroid by, call it a millimeter per second, and it's enough to make an asteroid miss the Earth, I'll reverse the question. How accurately do you need to measure the velocity of an asteroid to know if it's going to hit? The answer is about a millimeter per second. So a lot of what we do at the Asteroid Institute is we work on means of doing orbit determination at scale. Calculate it if you're going to discover millions of asteroids, you need to discover a way to calculate their orbits, millions of them at a time. Okay, and in large part, that is figuring out ways to run that calculation much more efficiently and faster and parallelizable as possible. So, it's actually rather amazing that when we measure the location of an asteroid and we fit its orbit, we're actually determining its velocity to something like 10 to the minus 5 kilometers per hour. So a millimeter per second. It's amazing, right? This thing is out, 150, 250 million miles from Earth, and you're spotting it on a single pixel, and we're going to measure its velocity by calculating its orbit to a millimeter per second. And that's commonplace. So I don't want to leave the impression that these things are easy. These things are very, very difficult. People like our group over here specialize in making those types of calculations fast, easy, repeatable, and doable by all in an open source manner. Sure. Oh, okay. All right. I'll take you and then you.
Okay, so when my kids were little, I recall they played this little video game where there was a bunch of little bubbles on the screen. And then you would steer one of the bubbles into another bubble, and that bubble would grow and so on, and try to get a bubble as big as possible. So my question is can you use that sort of technique to kind of clean out the asteroid belt?
Question is, can you clean up the asteroid belt by steering things into each other? It's very, very difficult because the velocities that they would hit each other is very high. If you're not in the same orbit, and even if you cross at 1 degree, 1 degree is about 1/60th of a radian, so the velocity difference is whatever your orbital velocity is, call it 60,000 miles an hour times 1/60th. Oh, well, you're still talking 1,000 miles an hour. It's still really fast, right? You can't just they don't just like touch and merge. Every collision in space is big and violent. So I don't think we'll be able to clean up the asteroid belt, but I think we can measure where everything is. That's the consolation prize, I would say. Oh, okay. Oh, the guys who went to school with me at Cornell. Well, we have Bill here, who was an engineer with me at Cornell, and we lived in a house together. We drove across the country multiple times together, and we've known each other for 45 years, we decided. My friend Derek, who is floating around here someplace back there, also known for 45 years. We go way back. Paul is around here someplace. Where's Paul? There you are. And Jeannie, Paul was my roommate at Stanford, but we also knew each other around the same time back at Cornell, and I was at their wedding. Let's see. I think that's all from Cornell here. Anybody else from Cornell here? Go Big Red! Yay! I did want to come back a little bit to this question about the engineering of the solar system. I do think it's kind of remarkable that what we're actually talking about doing when we're talking about deflecting asteroids from hitting Earth is slightly engineering the solar system such that the third planet from the sun no longer gets hit by large asteroids. Now, this has been a process that's been going on since the beginning of the solar system for 5 billion years, but us hairless monkeys living on the third planet have devised the technology to prevent that third planet from being hit by asteroids at that point. That's actually fairly amazing if you think about it. We are actually there right now. And so don't lose sight of that, of just how awesome that is. Really, we're reaching out at things that are hundreds of millions of miles away, and we're tweaking around so that this planet doesn't get hit. That's kind of cool. Dan?
Other than mapping the hundreds of millions of miles of the solar system, what has been the greatest challenge that you've faced, and how have you done it?
So the greatest challenge we faced, apart from the technical challenges, is the question of what we're trying to do. For a while, when we started all this business, it's been nearly 20 years, it was getting people to take it seriously. Because around that time, people weren't certain that what killed off the dinosaurs was an asteroid impact, and they kind of laughed about it. And a couple things began to change people's minds. Number one, Comet Shoemaker-Levy, which hit Jupiter, leaving in 1992, I think it was, leaving the explosion area on Jupiter was larger than the Earth. So you can immediately go, wow, if that hit the Earth, that wouldn't have been good, right? Then we had a series of bad movies in the late 90s, including Armageddon, and another movie called Deep Impact. At least it got people thinking a little bit about it. But then in 2013, we had a small asteroid, just 19 meters across, hit near the Russian city of Chelyabinsk. About 30 times the energy of the Hiroshima bomb. Very high altitude, about 50 kilometers from the city. Luckily, it was about 50 kilometers from the city, because otherwise we would have been looking at perhaps 1 million casualties. It's a good-sized city. It broke every window in the city, put a couple thousand people in the hospital, collapsed some buildings, but it was 50 kilometers away from the city. So, here to I don't know what's 30 miles away from here, somewhere's up in the Everett. Okay, so it got people really to, and because there was enough video of it, it was sort of visceral, and it was in the age of social media, so you could see images. And that's when the congressional hearings started. That's when me and others had to testify, and there was a lot less joking around about it at that point. And I think what we're going to see here in the next coming years as Rubin really comes online is you're going to see us hopefully take these things seriously. Because it would really be a rotten way to go if we got hit by an asteroid and we just because we did nothing about it. Okay, last question, and then I'll drink beer with anybody here. So.
Similar to like large scale agriculture projects or damming rivers, that kind of thing. What do you see as the equivalent of that at a solar scale, at like the scale of the solar system?
Yeah, I mean, what kind of engineering is there on the large scale, right? I think in some sense, like, humans have been doing geoengineering since, well, since humans have been around, since we've been doing agriculture, we've been doing this, right? We do irrigation, things like that. Other animals do too, beavers, they make dams. But what we're talking about here is the first sort of solar system-wide engineering from the standpoint of protecting your planet. I did want to come back to your question earlier about what was hardest about it. The interesting thing, even though there has been this shift, is that for the longest time we've been just out there shouting in the wilderness that somebody needs to take this thing seriously. And we at the B612 Foundation have really, we're a nonprofit. Because it's very difficult to come up with a business model. Saving the earth doesn't pay. It's true. You can't build a business around that. So we've been a nonprofit, and we get by with our roughly 8 people on private donations each and every year. That's actually been the hardest thing of keeping all this afloat, is actually paying for our 8 people. It's not that big, but we have to make payroll. So that's the truth about that. So first off, thank you, everyone. Come talk to Colleen or Mario or Joachim or Kathleen if you want. I'll be here drinking my beer. And thanks for coming along. Shut this down.
All right. Let's give him another big round of applause. So while I get the trivia set up real fast, I'm going to introduce Colleen from the B612 Institute to talk a little more about the Institute and some cool stuff you should follow up on.
Yeah. I don't want to keep you too long. I just thank you all so much for coming tonight and hearing Ed. He has an incredible story and he keeps going, and everything from what he did up in space to asteroids to any type of Mel Brooks movie. He's just got it all in a catalog in his head. So really great having you, Ed, and coming up here. So thank you. For everybody who's interested in the Schweikart Prize, there's actually a flyer up here. This is for anybody who's post-grad. Is eligible for innovative ideas for planetary defense. It's true that you get to meet our other co-founder, Rusty Schweikart, the Apollo 9 astronaut. If you get to a certain phase within your proposal, they are just opening it up for applications right now. And the cash reward is $10,000. It'll be in its 3rd year awarded to a student. Last year was a team. You can apply in as a team, and so if you think you have an idea that maybe nobody else has thought of, I suggest you come up here and grab a flyer. We also have a QR code. You can sign up for our mailing list. For anybody else, you can go to the website and do it that way. And we have some other brochures, and please take our 2024 annual report with you. That's all I have. Thank you again for coming. Back over to you.
Thanks again, Ed and Colleen. I'm going to go over the trivia answers real fast and then announce the winners. So our answers for tonight, for question 1, it was the STS-112 Atlantis that did not include Dr. Ed Lu as a crew member. It was the Soyuz one, and there is a little bit of a trick question because it doesn't follow the pattern. Question 2, he served as a member of Expedition 7. It's a good number on here. The B612 Foundation takes its name from, in fact, the asteroid home of the Little Prince, which is a fun fact that I didn't know about. One of the many major difficulties in predicting long-term asteroid trajectories is uncertainty in small non-gravitational forces, such as the Yarkovsky effect. There are several people here you could talk to about that more if you're interested. Question 5, The Atom platform is primarily designed to simulate orbital trajectories and detect potential impactors. It's very cool. One major computational challenge in astrodynamics today is handling massive data sets from survey telescopes in near real time. This is especially true with the Vera-Rubin Observatory that will give us unprecedented amounts of data. Asteroid mapping and tracking also have growing economic importance because they can identify potential targets for mining rare materials. As Dr. Liu said, the asteroids have oh, that's fun. Stuff that you could potentially get to as we become a more spacefaring civilization. Question 8. When astronomers first determine an asteroid orbit from telescope data, the typical first step is linking multiple sky detections to a single tracklet set. It depends on who you ask. There might be a couple different first steps, but this is typically what happens, I'm told. I don't work on asteroids. Question 9. A 100-meter asteroid striking Earth is roughly comparable to a modern thermonuclear test. This is a very, very large explosion and would be a big problem for everyone on Earth.
It's about 100 times larger than that.
He says it's about 100 times larger than that. So, crazy stuff. And finally, question 10, the term accessible astrodynamics most closely refers to open source tools that let anyone simulate orbits online, like Atom, for example. So, those are the trivia answers. And our winners today, we have 1 winner and 3 second place teams. So the 3 second place teams, all with 8 points, are Ethan D. Is Ethan D here? Yeah, good job. And if you are one of our lucky winners tonight, you should come up to the front afterwards to collect a prize that we have. Another 8-point team is Team We Did Not Cheat. That are definitely not astronomy undergraduates from the University of Washington. And our other 8-point team is Gilly Fank. Good job. And in first place, a team with 9 points is a mystery. Congratulations. All right, so if you are one of the lucky winners, please come up to collect your prize. And thank you all so much for coming. Thank you all for listening to our talk. As a reminder, our next event, oh, this slide doesn't have it. Our next event will be, going all the way back, will be on November 19th at 7 p.m. at Wheelie Pop Brewing, not here. It'll be at Wheelie Pop Brewing, which is in Ballard. We hope to see you all there. Thank you so much for coming. Get home safely.